Hello, my name is Dongchan Kim, and it is a great pleasure to be here. I'm going to talk about my research, configuration-specific hysteresis modeling of tendon sheath mechanism with RNN and Presac model. The tendon sheath mechanism is used for manipulator control in most flexible surgical robots. Due to the change in the magnitude of hysteresis for displacement transmission according to the shape of the TSM, it is difficult to accurately control the motion of the manipulator. This study aims to develop a hysteresis model applicable to the arbitrary single curved shape of the TSM. To this end, we devised a learning model that combines the Presac hysteresis model and RNN. A single curve is defined by two parameters: the curve angle and the radius of curvature. Experiments were conducted to measure the output displacement according to the input signal for 24 shapes combined with 6 curve angles and 4 radii of curvature shown in the table. The picture on the right is the experimental setup. From the experimental results, the magnitude of hysteresis is proportional to the curve angle and inversely proportional to the radius of curvature. Of the 24 sets of data, the data for 18 shapes were classified as the training set, and the data for 6 shapes were classified as the validation set. The parameters marked in blue in the table are intermediate values of the parameters of the training and validation sets. Among the shapes made with these parameters, the data of 5 shapes were used as the test set. The Presac model models a hysteresis loop through a weighted sum of the output of a mechanical play operator gamma that can be described as a piston cylinder model. In the video, a hysteresis loop is formed through the weighted sum of the outputs of 10 piston cylinder models with different lengths of the cylinder. The figure shows the structure of the learning model that combines the Presac model and the artificial neural network. The input signal goes through 11 mechanical play operators with different value of P and outputs from Y1 to Y11. After standardization and data augmentation, they are grouped into 10 time intervals and input into 11 LSTMs respectively. The shape dense layer receives 2 standardized shape parameter data. The distal dense layer receives output of 11 LSTMs and the shape dense layer. The last node of the distal dense layer estimates the output through a weighted sum. For one of the test set shape, the output of the learning model and the experimental data were compared. This shows that the learning model can be used for hysteresis modeling of the arbitrary single curve of the TSM. Thank you for listening.